All right, we're ready to get looking at some AC power here. I'm filling in for Dr. Hartman today, and he'll be back on Monday. So when we look at these power problems, first thing you got to ask yourself is, are they asking me for instantaneous power or average power? So we got the two terms here. Instantaneous power, of course, is power at some function or some point in time. Sorry, power at some point in time. So if you see something asking you, find the power at 10 microseconds, like problem 2 in the N class today. Well, you know, since they're asking it at a particular point in time, we got to be looking for instantaneous power. Or an expression as a function of time, like in class number 1, where we're asking for P of t. Okay. So that would be an instantaneous power type problem. Average power, on the other hand, doesn't involve time. So average power is just a number. We usually just write it as P sub AVG, or just P, really. We're going to get to next week saying that we're just going to use P to talk about average power. So it's just a number, some number of watts. Okay? So that'll be key. And for instantaneous power, if they're asking us for P of t, you can always find it if you know the voltage at that point in time, and you know the current at that point in time. You can multiply the two together, and you can get the power at that point in time. So, I mean, that's always one thing. If we're working in the frequency domain and we've got our magnitudes and our phase angles, you go back to the time domain. You can create the time domain function. You have all the information you need if you know magnitude and phase angle. You build the time domain function, you stick in the value of time, you get the instantaneous voltage for that thing at that time, the instantaneous current for that thing at that time, and you multiply them together, and you've got power for that thing. So that's one way to do it, and that always works. Okay, so we can do that. The rest of this is using trig identities to come up with alternative ways to do this, right? Dr. Hartman mentioned in the video for today that if you look at these two functions, both cosine functions, different phase angles, theta v, theta I, different magnitudes, then you can use a trig function that splits two cosines, the product of two cosines apart, into, let's see, the sum of the two cosines, half of the sum of the two cosines plus half of the difference in the two cosines. So you end up with this equation that he had where you have Vm, Im, cosine theta v minus theta I, and then you have 1/2 Vm, Im, cosine the sum, which is 2 omega t plus theta v plus theta I. Okay? And so this, again, is always a good equation. This works. This is just the expansion of the first one into magnitudes and phase angles. You notice the first part here, as he mentioned, has no time component. So this is just a number. This is the DC part of it, and this is average power.
So that's a 2 omega t plus theta v.
Plus theta I. Yeah.
Okay, thank you.
This part here is the AC part. This is sinusoidal at 2 omega t. It's the sum of both of those two expressions, so it's running at 2 omega t. Okay, so the instantaneous power includes an average part and the sinusoidal part riding on top of it. And whenever we ask for just the average power, we're just asking for this DC part, the average part that it rides on top of. Okay, so this is also a good expression. And then further shortcuts. If we're looking at just a resistor and we're talking about the instantaneous power absorbed by a resistor, well, there's a couple of things we know about a resistor. We know that theta V equals theta I at a resistor. Whatever the voltage is across a resistor, when you go to find the current for that resistor, you just divide the phasor, the complex number, by R. You divide it by a real number. It doesn't change the angle at all. A resistor doesn't have the power to change an angle. It changes the magnitude, but the angle of the current stays the same as the angle of the voltage. So whatever it is, whatever the phase angle of the voltage is, the current is the same, and vice versa. You got the current with its phase angle, you multiply it by R, and you get the voltage across it, it's still at the same phase angle. So theta V equals theta I, which means theta V minus theta I is 0, and cosine of 0 is 1. So boom, for the first term, you just get 1/2 Vm Im. Okay? So instantaneous power, when we're talking about a resistor, works out to be 1/2 Vm Im for the first part. So that's where we get the 1. And then the second part is just 1/2 Vm Im times cosine 2 omega t plus theta V plus theta I, where theta V equals theta I. So you're adding the same number twice. We leave it like that to show we have Vm and theta V, we have Im and theta I. So we're just using those numbers. If we just know the voltage across the resistor, then just like in a DC circuit, we can use a shortcut and say, well, that's 1/2 Vm squared over R times 1 plus cosine 2 omega t. Now this time we've just got Vm, so we would theoretically just have theta V, so we'd say 2 theta V. Theta V, and knowing theta I is going to be the same thing. Or we could write it as 1/2 Im squared times R, 1 plus cosine 2 omega t plus 2 theta I, where we know Im and theta I. So we've got various forms here that we can use to find instantaneous power right across a resistor. Okay. Again, that's all in the video, so it's all there. If you want to go back and look at that and pause it and copy it down. If we looked at an inductor, right? The whole point of the lab that we did on Wednesday was to show the relationship between the voltage and the current right across an inductor, and then turn around again and do it across the capacitor. And what did we see that was the relationship between voltage and current across an inductor? They're 90 degrees apart, right? You did the math. We converted to omega t radians. We converted radians to degrees, and it should have come out at 89.9 or something, which gets us right at 90 degrees, right, with the rounding errors. So for an inductor, theta V equals theta I plus 90 degrees. Okay. The current in an inductor lags behind the voltage by 90 degrees. Okay. And that means when we do this difference, theta V minus theta I, we get cosine of minus 90 degrees, which is 0. Okay. So instantaneous power for an inductor equals 0. There is no average part for the instantaneous power in an inductor, plus the second part, which is 1/2 Vm Im cosine 2 omega t plus, in this case, we could say 2 theta I plus 90 degrees. If we let theta V equals theta I plus 90 degrees plus theta I. We could get that, or 0 plus 1/2 Vm Im cosine 2 omega t plus 2 theta V minus 90 degrees, since theta I is theta V minus 90 degrees. So, all right. So the key point here, no average power in an inductor. Okay. And what do we mean by that then? Now we have to sort of explain what do we mean by average power? What are we calling that? And it turns out when we use that term, what we've allocated it for is power that's used to convert from one form of energy to another that you can't undo. Okay. So in a home, in a business, wherever you have resistors turning electrical energy into heat, that energy is transformed and it's gone, right? When you fire up a dryer and dry your clothes, the heat is used to dry your clothes, and then the heat goes into air, and then it's gone. When you cook something on a stove, you're using up that power, and you can't get it back. You've used it. That's why you pay for it. When you pay an electric bill, you're paying for everything that was converted from electrical energy to thermal energy. Lights, stoves, hair dryers, clothes dryers, heaters, everything. Okay? You've used it. You've consumed it. You did something useful with it, I hope. You cooked scrambled eggs for breakfast, and you got to pay for it. Okay? So when we talk about average power, next week we're also going to call it real power. It's the power you use up in day-to-day living, and it has to be paid for. Okay? Now, inductors and capacitors, they don't do that. They don't convert electrical energy to thermal energy and heat up stuff. The way they work is they store up energy, and then they turn around and release energy. So they don't actually use any of it. They borrow it, if you will, and store it up, and then they turn around and release it back into the circuit. So as far as the net usage, there's nothing. That's why their average power comes out to be 0. There is power being absorbed and released and absorbed and released. And so we're going to need to talk about that. And we're going to talk about it on Monday, and we're going to call it something else. But we're not going to call it average power or real power. We'll just use another term. Okay? So for that thing that we call average or real power, inductors and capacitors don't have any part of it. Okay? They do have this sinusoidal part at twice the original frequency, and that's here. So for capacitor, same thing. Theta I equals theta V plus 90 degrees. The current leads the voltage by 90 degrees in a capacitor circuit. So same thing there. The first term, the average power term, is going to have a cosine of 90 degrees in it. That's going to be 0. And then the second term is going to be there. So power, instantaneous power for capacitor, 0 plus 1/2 Vm Im cosine 2 omega t plus, here we would say 2 theta V plus 90 degrees, or 0 plus 1/2 Vm Im cosine 2 omega t plus 2 theta I minus 90 degrees. And all of these are watts. All of this power that we're talking about here are watts. Okay. And again, no average power in a capacitor. Okay.
That's 0 plus at the beginning.
Say again, I'm sorry?
Is that 0 plus at the beginning of each of these formulas? Okay.
Yes, that's the average power. Yes. All right, so mentioned the first in-class problem today, asked you to come up with an instantaneous power expression. It's for a circuit that has a resistor in it and a capacitor, if I believe, right? And it gives you the current going through it. So, we want to talk about the instantaneous power for this whole circuit. So a good thing to do would be to find, the voltage across both of them. This R here is 10,000 ohms or 10K ohms, and the capacitor is 200 nanofarads, and I of t is 2 sine 377t plus 22 degrees milliamps. So that would also be 0.002 cosine 377t minus 22 minus 90 is minus 68 degrees, I believe, amps. Okay, so we'd convert that, right? And we could redraw this thing then in the frequency domain and say, all right, well, what we really got is a resistor and an impedance. The I going through here is 0.002 at minus 68 degrees amps, 10,000 ohms, and J omega L, of course you know how to do this. Omega in this case, it's told us is 200,000 radians per second. So J omega L comes out to be J 3,000 ohms. And we need to know this voltage here across all of it. So you just multiply I times the impedances in series. 10,000 plus J3000. Okay, and you can get V. Right? And in the frequency domain over here, then we'd have Vm at angle theta V, and we've got Im at theta I, and that's all we need. Now we come back to the time domain, and you can write out the expression for instantaneous power, going right back up here and looking at this first equation. Vm, Im, theta V, theta I, omega, it's all here, right? So you just build yourself the instantaneous time or instantaneous power expression in time for that circuit. Okay. I'm sorry, I did that wrong. I was looking at the wrong problem when I did that. What did I do there? I'm sorry. I don't know what I was looking at. That was from memory. That's bad. I was working from memory from the last problem. They're told us here that Z equivalent, I'm sorry, Z equivalent is from this, the 10,000 and the 200 nanofarad. And it has this big old expression for that. So you want to practice putting that into your calculator. Make sure for this one that it comes out to be, I need to look at the right piece of paper, 7.984 at an angle of minus 37.016 degrees K ohms. Okay. That's from the expression of Z equivalent that was given. So that means we've got a voltage across that thing, this Z equivalent of 7.984 at minus 37.016 degrees K ohms. And I coming down into this thing is the 0.002 at minus 68 degrees amps. Okay, so I times that Z should give us the V, and then we can go back and come up with our power expression. Okay, so again, it's asking for P of T back over here, and we've got an equation for that. It's the second one that I was actually working in my head. The second one says we've got a current source in parallel with a resistor in parallel with an inductor. And they're in the time domain, the description of them, but we need to do our work in the frequency domain. So we come over here and they told us this one, the cosine function for the current. So it's 100 milliamps. So that's 0.1 at 0 degrees amps in parallel with a 1000 ohm resistor in parallel with a 15 millihenry inductor. This is the one that's at 200,000 radians per second. So this is J 3000 ohms. Yeah. And we're asked to find the instantaneous power. So we've got to come up with a P of T for each of these things at T equals 10 microseconds. So for each one, we got to know the voltage across it, and we got to know the current through it, so we can go back and use create our power equation and figure out what the P of T is at T equals 10 microseconds. So ultimately, we have to know this V, voltage across everything. These three things are in parallel. So we got to know the voltage. We've got to know I down through the resistor. So we got to know IR, and we got to know IL over here. So got to find those things. Okay. So you can do that. Yes, 1000 ohm resistor. So you can do current division. If Dr. Hartman was here, I'm certain he would do current division. He loves current division. Okay. You could also combine these two impedances in parallel and multiply them by this 0.1 at 0 degrees. get yourself the voltage, and then use that voltage to get each current. That's actually the way I like to do it. So different ways to do it, but you got to find V, and you got to find IL, and you got to find IR, right? And then you can go and come up with your equation, P of T for each one, and figure out what the power is going on at this 10 microsecond time frame for each one of them. Okay. If you're actually going to be putting this in your calculator, right, and figuring it out with that cosine 2 omega t term in there, plus theta v, maybe plus 90 degrees or whatever, you know, then you're going to have a mess, right? Because 2 omega t is going to be in radians, and right there inside the parentheses, plus 18.353 degrees. So right away, you can't do that. Radians and degrees. So you're going to have to convert. I would suggest converting the radians to degrees. Then you can add the degrees together. Then you can take the cosine of that thing, all in your calculator. But you got to do a units conversion before you can even move forward. Then add in the rest of the stuff, multiplying by VM and IM and adding to the other stuff. Just so that's in the middle of all that. Is this radians and degrees within the same parentheses, for Pete's sake. So just nature of the beast. Okay. This problem, just again to tie it back to the video, like Dr. Hartman did, if you find V here like I did and worked it, then what we're really finding here, right, for the source, this current is leaving the plus terminal. So when we find the power there, instantaneous power at 10 microseconds, that's really power being supplied. The current is leaving the plus terminal, and it's the only source in there. It's got to be supplying the power. The problem asks for the current, the power absorbed. So you could find it being supplied and then just put a negative sign on it. Say, okay, it's doing the opposite of supplying. In the video, Dr. Hartman looked at it and said, oh, they're asking for power absorbed. I'll turn the current around, and I'll make the current go into the plus terminal. Here we could have turned the voltage around and made the current go into the, leave the minus terminal or go into the plus terminal, because that's what they're asking for. So that's why he did it that way in the video. He sort of did it on the front end and prepared the problem that way. He knew what was coming. I do it this way, and then at the end say, oh, they want power absorbed. I found power supplied. We'll flip it. Just put a negative sign on it. And so I find these things out at the end and deal with them. He plans ahead and works that way. So again, either way, they both lead to the same answer. So that's why he did that in the video of intentionally reversing the direction of the current so that he could find power absorbed. You can't just find also power supplied, then flip that over. Put a negative sign on. Okay, so that's the second problem here.
What happened to the 15 milliamperes?
It became a J3000 ohm impedance. All right, and the third problem in this one asks for average power. So first two problems asking for instantaneous power. First one expression, second one an instantaneous value at a particular point in time. The third problem, already in the frequency domain, asks for average power. So that's the P part. So minus J2 ohms here, 4 at 30 degrees volts, 4 ohms, and 12 at 0 degrees amps. Okay. So in this problem here in the frequency domain, we would need to find this voltage here across the current source. We got to know it so we can move forward. That's also the voltage here across the resistor. Once we find it, that'll help us there. We need to find this voltage here, V minus J2. And then we need to know the current going down through the resistor. And we would need to know this current out here, maybe I1 we call it, and maybe going that way. Doesn't matter. We've got to know it, so in either direction. That way we would know the voltage across everything and the current through everything, right? This one here on the end, the current is going into the plus terminal of the voltage source, so that would be power absorbed. The two impedances, power absorbed. And over here, the current is leaving the plus terminal on the current source the way I've got it laid out. That would be power supplied, so we'd need to flip that over because the problem is asking for average power absorbed by everything. Again, that's just nomenclature of the problem, okay? For this one, right, we're finding P, that's capital P, the average power. So that's just the 1/2 Vm Im cosine theta V minus theta I. For each thing, we need to know the Vm, the Im, the theta V, and the theta I, right? Now, one of them is pretty easy, okay? The minus J2 impedance up there, that's a capacitor. I don't know the voltage across it. I don't know the current through it, but I guarantee you the phase angle between the two of them is 90 degrees, right? That was our lab the other day. It'd be the orange line and the green line on that graph that we looked at, or the oscilloscope. And so the angle between the voltage and the current, whatever they may be, is 90 degrees on that minus J2 impedance up there. So I can tell you right away, P for minus J2 is 0. Don't even have to find it, because when they turn out to be the 90-degree phase shift and we do the cosine of theta V minus theta I, cosine of 90, 0, we're done. Okay? So just work on the other three. So good thing to know that the average power in an inductor or capacitor is always 0. Okay? So, for the others, just find the voltage across them and the current through them, and then do the equation Vm Im, 1/2 Vm Im cosine theta V minus theta I. Okay, so that's average power that's asked for in that third one. Okay, we are going to do average a whole lot. I mean, the instantaneous power, it's not worth a whole lot, right? It's the power at some point in time. And when you talk about a circuit, you like to talk about how it works all the time. So we like to use these average numbers and say, okay, the average power in that circuit is so many watts. The average power being supplied is so many watts. We're going to end up talking a whole lot more about average than we are about instantaneous. And when it comes to average, there's a value we need to talk about, because, you know, when we have a circuit like this, or a waveform like this, a sinusoid with equal area above and below the x-axis, the average is 0. And it's not going to do us a whole lot of good to talk about averages if the average of everything is 0. So we need a different value or a different computation. And so we've come up with this thing, or there is this thing called measured value. It's also sometimes called effective value. And we're not making this stuff up. I mean, we don't make up much stuff. We do some things, but most stuff we get from mathematics, right? We actually borrow good stuff from our friends in the sciences, right? And so this thing we come up with here is a mathematical operation, and it's used whenever you have positive and negative things that you can't just sum up. You did this in freshman engineering when we had the least squares linear regression thing. We tried to draw a line between a bunch of data points, and the error was sometimes positive and sometimes negative, depending on whether the point was above or below the line. And if you just add up the error, then you could easily get 0 error for a line that doesn't go anywhere near the points. Just so happens that the positive error and the negative error cancel each other out, and you say there's 0 error. So it was meaningless. So what did we do? We squared it, right? When you square all the errors, then you make everything positive, and now you got something you can talk about. You minimize that amount of error, you've actually got something legitimate. So we do the same thing here. If this was some voltage and we wanted to talk about this new value, or this sort of average value for it, we could square it. We could take V of t and square it. That gets everything positive, right? And now we want to know how much of that we got, so we integrate that over one period, find out how much there is in that period, and then divide by the period, or multiply by 1/t, and now we've got the average of the squared function, right? And since we squared it, we undo that by taking the square root of it. So what we have here at the end of the day is we've squared something. So we have a square. We found the average of it by integrating and dividing by the amount of a period. And that's also called a mean, right? An average and a mean are the same thing. And then at the end, we took the square root of it. So the mathematical operation we've done here is called a root mean square. And while that's fun to say, we abbreviate it as RMS. So a measured value or an effective value is also an RMS value. And we do this mathematical operation on it and come up with this measured or effective value of this waveform that has both equal to positive and negative areas. So it would have an average of 0, but have a non-zero root mean square function or value. Okay? Now, the math here can get kind of ugly. It's depending on what you're squaring. Some things you square them, it's not too terrible. You can still integrate it and divide by the period and all that stuff. Other things, like a cosine function, when you start squaring it, things get bad in a hurry. And then when you want to integrate it, well, then it just gets plain ugly, right? So fortunately for us, somebody did the math at some point. I think Dr. Hartman can do it. I don't do it. But for any sinusoidal waveform, and that's us most of the time, the RMS value of anything, so in this case VRMS, is to find its amplitude or its maximum value and divide it by the square root of 2. And we never have to do the math again, or in the first place. And that's kind of nice, because I can divide by the square root of 2. Well, actually, this can. I can't. You know. So that's it for us. For the most of the things we work with, find the peak divided by the square root of 2, and you've got its effective value. Okay? So that'll come in handy in the web work when we go look at that for a minute. It also means that if we looked at our power, average power equation, that was 1/2 Vm Im cosine theta V minus theta I in watts. We could rewrite this as Vm over the square root of 2 times Im over the square root of 2. That's the same thing, right? Square root of 2 times square root of 2 is 2. It's in the denominator. So cosine theta V minus theta I. So we could rewrite this equation as VRMS times IRMS cosine of theta V minus theta I. So as we get into it next week, and we're working more and more with these AC circuits, and we're working more and more with RMS values, then when we go to our P equation, it just shrinks down to VRMS, IRMS, cosine theta V minus theta I. So we don't even have to use the magnitudes of our sinusoidal waveform. We can use its effective value. So that comes in handy. We even go further and say that this angle, theta V minus theta I, we do it so often, finding the voltage minus the current phase angle, that we give it a name. We call it theta P, which is the power angle. And so this equation shrinks down even more to VRMS, IRMS, cosine theta P. And so we're going to use it so much that we say, all right, right there for that thing, resistor or voltage source or whatever, what's its power angle? What is theta V minus theta I? Because we're going to need it a whole lot. So we go ahead and get it and put a name on it. So we do this. It also means if we're just looking at a resistor, which is where all of this P is used up, right? There's P in every voltage source, there's P in every current source, but in the circuit, the only thing that uses up power is the resistor, right? the real-time power, the average power for an inductor is 0, and the average power for a capacitor is 0. So all of the average power in the circuit's used up by the resistors. So that's where we're going to go a lot, is look at the resistors. And remember, for a resistor, theta V equals theta I. Theta P equals 0 degrees, because they're sitting there at the same phase. So the real-time power, or the average power for a resistor, P sub R, just comes out to be V RMS I RMS. It also means we can use our shortcuts, right? From before, because before when we had P equals V times I, then we said, oh, that's also V squared over R, or I squared times R in a DC circuit, right? So we could write this as V RMS squared over R, or I RMS squared times R. Which means we could also write it, since VRMS is Vm over the square root of 2 over the R, we could square that. Or IRMS is Im over the square root of 2 squared times R. Then we could write these as, let's see, this would be Vm squared over 2R, if we squared it and then move that in the denominator, or Im squared times R over 2. Again, that's real-time power for a resistor, or average power for a resistor, if we just know the voltage or the current and the resistance. So let's look at this in a circuit problem, then just sort of see how these things play out. If we have a circuit here with 2 current sources and some impedances, suppose this one over here was 1.6 at 83 degrees amps. And this one over here was 2 at 20 degrees amps. And suppose this first impedance was written as 4 plus J3 ohms. That's a rectangular form, complex number. It's got a real part, it's got an imaginary part. It's all ohms. And so what it really means is inside that box there, there's a resistor of 4 ohms and an inductor that has an impedance of positive J3 ohms. And they're in series, so we can add them together and treat it as one unit, because we can type 4 plus J3 into the calculator. Well, 4 plus 3I. So we can work with it as a complex impedance, as a box, if you will. And we're going to do that in the web work. So go ahead and throwing it out here, just so you can see it. This one is maybe 6 plus J2 ohms, which again just means a resistor and an inductor in series. And up here, 5 minus J5 ohms. So a resistor and a capacitor impedance in series. And suppose in this problem, we were asked to find the average power used up everywhere, or supplied everywhere, or supplied by the sources and used up by the impedances, or however the problem was phrased, but we need to find average power. Okay. So again, VRMS, IRMS, cosine theta P, which means for everything in here, every source and every box, we need either the voltage across it, so we know Vm and theta V, and we need a current through it, so we know Im and theta I. We got that, we can compute the power, right? So granted, that might take in these problems 20 minutes or so. It might take longer than actually finding the power, is to find all the voltages and all the currents, just so we can come along and then go boom, boom, boom and solve for the real-time power or whatever. Finding all the voltages and the currents is really the bulk of the job, okay? So but we got to know everything before we can do it with these AC power. So here, for example, we have two current sources. Both are coming up around the outside. So when they come together in the middle, they'll just add together and go down, right? So I could add those two together and get the current down the middle here, which I found to be 3.08 at 47.6 degrees amps. And now we know the current through all of these impedances. So we could just multiply each current by each impedance and get the voltage across them. Current enters the plus terminal, remember, of an impedance, just like current entered the plus terminal of a resistance of a polarity. So for a current coming down here in the middle, I found a 19.458 at 66.04 degrees volts. Up here for the 4 plus J3, the current's coming in from the left, coming around from this source here. So that puts the plus sign over here on the left. And this was 10 volts at 56.87 degrees. And over here on the right, the current's coming in from the right. So the plus sign would be over here on the right and the minus on the left. And I found this to be 11.314 at 38 degrees volts. And that's the voltage across each impedance. We got to know the voltage also across both current sources so that we can find the real-time power for each of those. So if we put the plus signs on top, we'd find the power supplied. But then if the problem asked for the power absorbed, we could just multiply it by -1. So that's okay, I hope. For these, we got to use KVL, right? We've got a loop here where we know all the voltages but one. So we can use the loop on the left to find the left current source voltage. We can use the loop on the right to find the right current source voltage. It's just, again, adding some numbers together in our calculator. I found this voltage here to be 29.37 at 62.93 degrees volts. And over here, I found this voltage to be 29.92 volts at 55.80 degrees volts. And after all of that, we know every voltage and every current, and now we can start working on power. And we're out of time, so we're not going to solve them all, but let's just look at one. If we were to find, say, the power, the 4 plus J3 box up there, say, let's find the average power for that complex impedance, 4 plus J3, right? We know the voltage across it. We know the current through it. Here's the voltage across it. Here's the current through it. So we can just go, right? 1/2 VM, which is 10 from up there, times IM, which is 2 from there, cosine of theta V, 56.87 degrees, minus theta I, which is 20 degrees, and punch that in the calculator, right? Everything's in degrees here now because average power doesn't involve time, right? So we don't have to worry about radians in degrees. Everything's in degrees. So it's 1/2 VM IM cosine theta V minus theta I. And we punch it up and it should come out to be 8 watts. So we would do that for everything in here, all 3 impedances and both sources. We could go through and find P for each of them. You might be thinking now, yeah, but there's a shortcut. And if there's a shortcut, I'm always going to take the shortcut. I'm never going to write out a long equation when I can use a shorter equation, right? You're all wearing these masks, so I can't tell, but I think that's what you're thinking right now, okay? So you might remember, all right, inside that 4 plus J3 box, there's a 4 ohm resistor and a J3 ohm impedance. The J3 is an inductor. P for an inductor is 0. We said that. It is. So really, all of this P right here is from that 4 ohm resistor. I could have just found the P for the 4 ohm resistor using these shortcuts right here that we came up with. Sorry, they were all right there. I know both the voltage across it and the current through it. So I could use those to find it. So I could have come down here and say, you know, really P at 4 plus J3 is really P at 4. There is no contribution from the J3. So I could have found the P at 4. Now, let's think about this for a second. You know, Vm, Im, theta V, theta I, we've got all of that. But when we look up here, this 10 at 56.87 degrees volts. What is that the voltage across? Is it not the voltage across that box? And inside the box is a 4 ohm resistor and the J2 ohm impedance. And so that voltage is across both of them. And now we want to go in and just focus on the resistor. So we need the voltage across the resistor. Do we know that? I don't have that written down anywhere, right? Could we find it? Absolutely. Is it hard? No. But do we know it right now? No. And so many people do these problems and they send emails and say, I'm using the voltage and I'm doing the shortcut and I get the wrong answer. Why? So here's where we got to look and say, okay, you don't really know the voltage across the resistor, even though you could go find it, but what you have there is not that. You've got the voltage across two things in series. Things in series form a voltage divider, so you'd have to break this thing apart. But on the other hand, you know the current through this box, and the two things in this box are in series. So do we know the current through the 4 ohm resistor? Yes. So we got all these things up here, half of which involve voltage and half of which involve current. So if we just limit ourselves to the shortcuts that involve current, we'd be okay. But if we try to use the shortcuts that involve voltage without doing any additional work, we're not going to be okay. So let's just use these that involve current, this one and this one. So Im squared R over 2. Im squared R, times R, divided by 2. Okay, which is the same as IRMS squared times R. Okay. Im squared over 2 is IRMS squared. Okay. So the magnitude, P for the resistor here, the Im is 2. So we'd have 2 squared, which is 4, over 2, times the value of the resistor, which is 4. So 2 times 4, 8 watts. So it is true that all the average power in that box is being used up by the resistor. And we can find it either by looking at the whole average power across the whole box, which we have the values for, or we can look at it by finding the current that's flowing through the resistor, which we also have the values for. We could also go find the voltage across the 4 ohm resistor and use that, but that's extra work, and who wants to do extra work, right? So we've got that, right? So you can use the shortcuts, just make sure that you're using something that you do actually know or have. Okay. And in the case when things are in series, you know the current. All right. So let's go look then and see how many like that we have in web work and see what's going on. My screen seems to have expired, so let me get this back. Okay. Not coming back, so just open up a new screen. All right. So on the web work problems for Monday, or over this topic, this should be 22. The first problem that comes up has absolutely nothing to do with AC power at all. So you may be asking yourself, well, why is it here then? It's an excellent question. Moving on, here it is. You just got to find this stuff. You're given IC and an impedance out here that you can convert to, a capacitance that you can convert to an impedance. And then you can find that voltage and use that voltage to find that current. You can work your way through this and find all these things. And ultimately, you got to find IR in phasor form so that you can turn around and put it back in the time domain, right? You need to know its magnitude and its phase angle, so you can put it back in the time domain. And so just some old stuff there and nothing to do about power at all. The next problem does have something to do with power. The next problem is just like in-class problem number 2. A lot of people ask about this one. Again, it's a word problem that always causes some interpretation issues, but it's worked just like in-class problem 2. That's why in-class problem 2 is there, to give you practice at solving this. So 3 things in parallel, and you're asked to find instantaneous power at 2.9 milliseconds. In my case, your time will be different, I think. So you got to do the same thing that we did in class 2. I got to get the voltage across each thing and the current through each thing, and then you can go. The third problem here has the complex impedances in it. So that's why we did this problem, so you can see what these things are, these boxes. And if you know the voltage across the box, like you do here, you know this voltage across the box, you can use that, or you can figure out the current through it. You need to know that anyway. And then you could use that to find P. This problem is asking for average power. Okay. So the last problem was instantaneous power. This one's average power. And the last one is also average power. So here, and then you're given 3 currents in graphical form and the value of a resistor. So right here, we need to go back and use some equation that involves just current and resistance, something in the form I squared R. Okay, these things, as you look down them, they're not sinusoidal. So IM doesn't come into play here. So IRMS would come into play here. Could we find the RMS values of these things? This is why we talked about RMS today. It wasn't in the video. It'll probably be in the video for Monday, but here's this homework problem. So RMS, we go back to that thing, square it, take the integral over a period, divide by the period, take the square root of that. That gives you its RMS value. If it's a sinusoid, great. The first one's not sinusoidal at all. So we got to square this thing. These are just some constant values, positive and negative. So when we square them, they'll all be positive, and we can figure out the integral, which again, there graphical would be nice. Area under the curve, be perfectly fine. Some of it's 0, so factor that in when you compute the period, as the period goes to where the waveform repeats itself. So past this 0 part would be in the first period, and do the math. And that one's not so terrible. Square it, find the area, divide by the period, take the square root. Okay. The second one down here, not constants anymore, first order equations. Okay, square those, second order equations. Straight lines become parabolas. Area under the curve just went out the window because can't find a graphical area under the curve of a parabola. So we got to do the math. And by we, I mean you. Got to do the math, right? And so with this one, okay, I got to come up with the y equals mx plus b form of these lines. Here's where you get to pick your period, right? As Dr. Hartman mentioned in the video, any period will work. Pick one that helps you. If you want to work here, the triangle in the middle, you've got to find the expression for this line, which has a y-intercept down there somewhere. And you got to find the expression of this line, which has a y-intercept up in room 212 somewhere. So, are they hard to find? No, but it's just extra work. What if we kept drawing this sawtooth function and moved over to this period, the one that goes from, in my case, -9 milliseconds to +9 milliseconds, right here around 0, where the y-intercept is right there, right there. Just here I am. And that's a whole lot easier to work with, right? So pick your period. It can be a full period. It can be 2 half periods. Be whatever you want. Just got to have a period. So if you work over here, things get a little easier. Something t becomes something t squared, and you got to integrate that. That's not terrible. So you do the math, average, square root, and then IRMS squared times R. This last one down here, Oh my goodness. It's already ugly before we even start. And you start thinking about, I got to square that, and then find the area of that, and then you look right up here, and right about here is where you say, there's a note here that says each one of these is part of a sine wave, and part is enough. It's sinusoidal. Shortcut works. Peak over the square root of 2. Done. Okay. Don't send an email. You could send an email on this one to Dr. Hartman. He can do the math. He's young, energetic. He likes doing stuff. I'm not about to do the math on this thing. I'm old and tired, and I'm not going to do it. Okay. I'm going to tell you peak over the square root of 2. And if you say, well, if I do integrate and all this, I'll say, I don't know. You know, knock yourself out. But I'm doing the peak over the square root of 2, and I'm going to the house. So that's it. This one's sinusoidal. The fact that it's a quarter of a sine wave doesn't matter. Peak over the square root of 2. All you need to know. Okay. So that's the RMS value there. Okay. And that's it. Any questions? Have a great weekend. Dr. Hartman will be back on Monday, and he'll be here all week. Anybody online got anything they need to ask about? Okay. Well, I think that's it then. So I'm gonna shut it down.